Welcome back to our course on Smart Grid System Monitoring and Control. In this module, we'll be covering voltage and reactive power management. The major topics that we'll cover will be an introduction to reactive power. How do we define it? Why do we need it? We'll then cover reactive power flow in some very simple networks. And then we'll discuss operating limits. We'll then cover a fairly novel pole and beam analogy for describing how the interaction of voltage and megavar injections and megavar consumption occurs in a network. And there are some very other simple analogies like the foam on a glass of beer or the wheelbarrow, but those are not very good when it comes to actually making operating decisions. I can assure you that this analogy will actually help you visualize the power system in real time and understand what's happening and make those decisions. Following that, we'll basically go through each type of equipment, all the way from generators to transmission lines, shunt capacitors to reactors, static VAR compensators, high voltage cables, transformers, and loads. And for each type of equipment, we'll be looking at how the reactive power consumption or contribution of that equipment varies as a function of the voltage. We'll look at the purpose of that equipment, if it's a controlling device like a transformer or a shunt capacitor, how does that help control voltage? How do the megavars of that piece of equipment vary as the power flowing through the equipment or as the voltage applied to that equipment? Equipment, basically, there's two types. There's equipment that has two terminals energized, and that could be a transformer or a transmission line, and their job is to pass power through the system. And then there's other equipment where one terminal is energized and the other is grounded, and their job is either to contribute megavars to the system, like a capacitor, or if it's a load, it's a device that is absorbing megavars along with the real power to do the work. So we'll cover each type of device from the point of view of how can that device impact or how can it be used and controlled to have good voltage control. Then we'll get into the whole phenomena of voltage collapse. In the power system, on most days, everything is very straightforward. The basic characteristic is voltages are high during the night because the loads are low and the transmission lines are having a charging effect and they're not absorbing megavars. What happens as the load picks up and we get to the peak, we have an issue with trying to keep the voltage high because at that time the loads are drawing lots of megavars and the transmission lines are highly loaded and they are a megavar load. And so implicit behind this is the fact that when you have an excess of megavars, the voltages are high. When you have a deficiency of megavars, the voltages are low. And basically, as an operator, your job is to keep the voltages within a well-defined limit at nighttime, make the transition during the morning load pickup, keep them within a limit from sagging during the peak, and then manage them, of course, as the load drops off. So it's very much a daily load cycle. Now, voltage control is a phenomenon where there's a lack of megavars, and basically your voltages just start declining. We've had cases where very peak load summer conditions with lots of air conditioning, the voltages will just start declining at like 1 kV a minute. A very, very disconcerting thing for the system operator to actually have that happening on your system. And our goal is to give you the tools to understand basically how to prevent that ahead of time, how to make sure your system is set up so you don't ever have that voltage collapse condition. And then there's another type of voltage collapse that occurs where you have a major contingency, a line trips out of service, it overloads the parallel lines, their consumption goes way up, and your generators start hitting their limits. And so you can actually get into a voltage collapse as a result of a contingency, and that can hit you fairly quickly. In fact, it can take several minutes for the actual voltage collapse to occur after a contingency, but basically it's happening so quickly you really don't have time to respond. So again, the underlying theme is you have to manage your voltages during the current conditions and every single contingency and certain well-defined multiple contingencies. So you've got to be in that preemptive or preventative mode of always looking ahead to think about what could happen if this outage occurs. And then through the presentation, we'll cover relevant NERC standards and we'll summarize at the end. So let's move on and look at reactive power. What is it? How do we define it? Why is it needed? And we'll cover the difference between real and reactive power, how real and reactive power vary over time with the AC voltage going up and down either at 60 cycles or 50 cycles a second. And we'll discuss a tool called the real and reactive power triangle. It's like the fundamental basis of a simple mental model that really helps explain what's happening in the system. We'll talk about how the AC current can be decomposed into real and reactive power components, and we'll finish up with a definition of power factor. There's two major tutorials that we'll use here. The EPRI Power Systems Dynamics tutorial has a very extensive Chapter 5 on voltage control. We'll be using a lot of the text and the figures from that. And then there's a very good chapter on voltage stability. And that entire document, as we've explained, is available as a PDF file for you all to download. There's another important reference that really takes the fundamentals in the EPRI tutorial to another level, and that is called Power System Voltage Stability by Carson Taylor. Carson is a life fellow of the IEEE, and he's devoted a significant part of his career to power system control. The current edition is out of print right now. The latest, you could get it on Google from $299 to $2,375. So this little book here has become a rarity, and so it's a real collector's item. If you have one, I'm very proud to say that I do have such a collector's item. But actually, I was talking to Carson this morning, and he is prepared to get a special issue if we can get a group together to order up to 20 at $60 a book. He can get a special edition printed, all from under the permission of McGraw-Hill. So it's an extremely good book. He's really captured a lifetime of experience. It has a documentation of voltage collapse scenarios all throughout the world, as well as a number that he was personally involved in analyzing at Bonneville Power Administration. So if we can get a collection of 15 students together, let's go to Carson and we'll get our own special edition, and then maybe you can sell it for $2,000. So, but again, it's a great book, and we'll be using some of the concepts from that. Now, so why do we need reactive power? Well, basically, there's two reasons. One is anytime we have a magnetic field, we have a current that has to serve that magnetic field. So induction motors have a magnetic field. Basically, there's a stator winding, and if it's a three-phase motor, we have a circulating magnetic field set up by that stator winding, and then that magnetic field induces currents in the rotor, and that rotor creates its own magnetic field, and then the rotor field is trying to keep up with the stator field. And it actually runs a little bit slower. It's called a slip factor, but basically that's an inherent part of why an induction motor works. We also have transmission lines. Basically, a transmission line has a current going through it, and we use the actual called the right-hand rule. The whole basis of the IEEE, you'll notice it's a little arrow with a circulating magnetic field. Well, that's the right-hand rule. What it means is that if the current is in the direction of my thumb, the magnetic field will be in the direction of my fingers. So let's think about what's happening in an AC conductor. The current is going up and down 60 times a second. So basically, for the first half of the cycle, it's increasing in this direction and flowing, and then coming back to zero, and then it's flowing in this direction and going the other way. Every time that waveform goes up and down, we're creating a magnetic field. The magnetic field is proportional to the current. So you can imagine that this magnetic field is growing and shrinking and then reversing direction as that current is flowing back and forth. So for the first half, it's growing in this direction, and the waves of flux are going that way, then it's coming back to zero, and the second half, the waves of flux are coming this way. So that magnetic field actually has energy in it, all right? I want you to think of two magnets with a north pole and a south pole. This is the magnet with the north pole, a magnet with the south pole. As you twist those magnets apart, that magnetic field has energy in it, doesn't it? If they were on an axis, and you twist them apart, then you let them go, they'd oscillate back and forth like that. So those magnetic fields have energy. So that is, but that energy doesn't get dissipated. That energy is available to oscillate back and forth. And another analogy I'll use is that, imagine a pendulum. As that pendulum comes up here and it swings back and forth, we're getting an exchange of energy between the potential energy of it being up here and then the kinetic energy as it's swinging. So I could have a huge pendulum with, say, you know, let's imagine we have a pendulum which is 100 feet long and then a 1-ton weight on it. There would be a huge amount of energy in that pendulum, and that energy is being exchanged from potential energy to kinetic energy. And all we have to do is inject enough energy into that system to overcome the friction. So you can get a huge amount of exchange of energy between potential to kinetic with very little real power loss. And basically, magnetic fields are one half of that equation, all right? The other part that we'll get into are what we call the electric fields. Now, there are other components that also have larger magnetic fields. Transformers, you've got this magnetic core. We can see it here. In this case, we have three phases, A, B, and C, and we have windings round around a very heavy, strong set of iron laminations. The reason for those iron laminations is that they increase the permeance much greater, thousands of times greater than air. So if I have, so the amount of flux that is going around in this core is much greater than if it was just an air coil. And that's the whole idea, is to increase the flux density, and that way you increase the effectiveness of one winding inducing voltage in the other winding. So transformers, as you energize them, they absorb megavars, and as you increase the power through them, they have a large megavar impact. And they are net consumers of megavars. A transformer, the megavars going in will always be less than the megavars coming out because they have a net loading effect. Now, synchronous generators, they have huge magnetic fields. Basically, you've got your rotor here. This is one that's been disassembled and is about to be put back together. And that rotor current has a DC winding on it, and it's got a DC current going through that winding, and then that DC current generates a huge magnetic field which basically comes out one side, goes through the air gap, goes through the iron core in the stator, and comes back in through that air gap. And it's that magnetic field of that rotor that is inducing the currents in the stator. And then those currents in the stator actually create their own magnetic field. Generators can be either producers of megavars or they can be consumers. In fact, generators have an extremely foundational role to play. They are like the rock of your system. They are the generators basically anchor the volt. They set the voltage at their level that you specify, and everything else in your system gets driven by that. If you were to raise all your generator set points, all the voltages in your system should go up together. So we'll be getting very much into the limitations of generators, what the minimum and maximum VAR capability is, and how that impacts the rest of the system. Now, we will cover the difference between real and reactive power. Real power is the megawatts. It's the active power that actually performs the work. It's the power that is needed to create heat, lighting, drive motors. So you're basically what's happening is your power plants are taking fuel, whether it's coal, water, gas, and it's converting it to electricity. Pretty much now, as we move into smart grid, things will change, but there's pretty much a one-way flow of power from your generators through the transmission lines to step-down transformers to the different types of customer loads. The losses in the transmission system are relatively small, around about 5%. So with active power, it's very predictable. If you have a transmission line and we're putting 500 megawatts in this end, I know I can't get more than 500 megawatts out at the receiving end. I'm going to get something a little, maybe 2-3% below 500. So from your SCADA point of view, you've got a good intuition. You will have a good feeling for how the real power is flowing in your system. You'll have a finite number of generators. Some will be close to your load, some will be distant, and you'll have an understanding that power flow is going to flow pretty much uniformly through your transmission lines to the consumption. And remember, we even covered in the previous module the line outage distribution factors, that if this line goes out, how much of that power flow is going to flow on the neighboring lines. You've got a fixed number of generators that are injecting your megawatts, and then you've got a certain number of substations that are stepping that power voltage down and then serving your customer loads and feeders. So again, you can get a very good handle on how the flows in your network are occurring and project that as the load picks up and as lines go out of service. With reactive power, it's totally different. It's a much harder quantity to really understand and visualize. We've had examples where people have commissioned their SCADA and state estimator systems, and they'll find many cases where the actual megavar flows are reversed. There's been something in the metering where the actual real-time flow that you're watching is reversed from the actual direction that it's flowing in. And it's only when you bring on your state estimator that you do the rigorous checking that you identify that. So what we're trying to do then is kind of give you a better intuitive understanding so that you can be understanding your system, looking at your SCADA diagrams, and making an assessment about what is reasonable. So we talked about the analogy with the pendulum. Basically, reactive power flows back and forth. The reactive power in a generator, now we need a convention, and our convention basically is if we have an inductive load at this end and a generator, and that's absorbing megavars, and a generator producing at this end, the direction of positive flow is from that generator to that inductive load. We covered that there's no energy used by reactive power exchanges, but it does load up the conductors with current. So as I have that current flowing through a resistance, I get a certain amount of what we call I squared R losses, and that's analogous to the friction I talked about with the pendulum. Now the other type of reactive power is capacitive reactive power. With capacitive reactive power, you're talking about energy that is stored in a magnetic field. Capacitors basically have two plates, and we store energy in that field by piling up electrons on one plate. So we've got an excess of electrons on one plate and a deficiency of electrons on the other plate. And as the voltage between those plates vary, the charge builds up on one plate and then it decreases on the other. So basically with a capacitor, you have your AC waveform picking up. So basically with a capacitor, as your current picks up, that a current is accumulating as an excess of electrons on one plate versus the other. And then as that excess of electrons builds up, your voltage goes up based upon the electrical charge. So the idea is that in a capacitor, the only way you can get a high voltage is to have an excess of electrons on one plate versus the other. And that leads into a lot of very challenging safety issues. You can de-energize that capacitor. You can basically open the circuit breaker and stop the flow of current, but all those electrons are still on that plate, and that can have an enormous flashing over impact and a danger. So just think of the shock you get if it's a dry day and you've been walking on carpet, you go up to, say, the elevator, and you touch that grounded, you get a definite shock that has an impact on you. The amount of charge that builds up on a capacitor is thousands or maybe millions of times of the charge that you had on your body, all right? So we'll get into the whole issue of what you have to do to handle with what's called the trapped charge on a capacitor. From an operator point of view, even though you won't be in the substation, you need to understand the types of risks and safety procedures your substation operators go through to deal with these special characteristics of capacitors. So basically, whereas in the mechanical analogy, we were talking about the difference between kinetic energy at the bottom, where it's going fast, and potential energy at the top, in the power system, we're primarily dealing with an exchange between energy in magnetic fields and energy in electrical fields. The magnetic fields are the inductive devices, like the motors, the transformers. The electrical fields are like the capacitors. Loads typically don't have an inherent capacitive ability. And so what we do in a power system is we put these additional capacitors in service to compensate for the actual magnetic fields that are drawn by the loads and the transmission lines and the transformers. Now, to truly understand what's happening from a dynamic point of view, let's zoom in and look at a voltage waveform. A voltage waveform basically goes up and down either 60 times a second in the US, North America, or 50 times a second in Europe, Japan, New Zealand. And so in North America, when we're looking at 1/60 of a second, that is 16.66 milliseconds. So our voltage waveform follows the sine function, goes on up, comes on down, crosses zero, and comes up again. And what we like to do for analysis, we say that whole cycle is 360 degrees. So what you can imagine, we're actually going through a rotation of 360 degrees 60 times a second. And we need this level of granularity to really understand what's happening, okay? So that's our voltage waveform. Our current waveform, if we have a resistor, is that our current, which would be the red curve, goes up and down perfectly in sync with our voltage waveform, peaking at the same time, crossing zero at the same time. Again, we call that totally in phase. We show that in a vector sense by saying that there's no phase angle difference between the voltage and the current. Now here's the essence. Power is voltage times current. To get power, you have to have a positive voltage, you have to have a positive current, and you multiply those together, okay? So in a real sense, in real time, we're multiplying the blue waveform times the red waveform. And look at what's happening. This purple, which is the mixture of the red and the blue code, it's zero when the voltage waveform is zero, the current's zero, and it's peaking when these both peak together. But look at what's happening. This waveform is actually running at twice the frequency of the original voltage and current waveforms. This is not a generally well-known fact, okay, that the power waveform is running at twice the frequency. It has to. And so, because even though we have the current and voltage applied in the reverse direction, we're still getting positive power out of that device, aren't we? Okay? So we've got an AC load, and even though we get positive power as the current flows this way, but we also get positive power as the current comes back this way. So by definition, our power waveform is peaking even when these two are negative. So it's going actually at 120 cycles a second. And there's a net average value. The net average value is right through here, and so we're getting a dissipation of real power in this circuit. Now, when we go to the situation where we have a voltage, AC voltage source going through an inductor, here's the waveform. We have a simple acronym. We say E for the voltage is leading the current when we have a reactive source. L is our symbol for a reactance. And so what we mean by that is our voltage wave crosses zero and rises at this point in time, and our current waveform is occurring 90 degrees later. So you see, our current waveform is crossing zero and increasing 90 degrees after the voltage. And we represent that in a vector form by saying that this current is lagging this voltage by 90 degrees. Positive rotation is these vectors are going in an anti-clockwise direction. Now, let's take the voltage and multiply it by the current waveform and look at what we get. When either the voltage or the current is zero, our product of voltage times current has to be zero. And so what we see is that our power, which is this purple one, comes on down because whenever one of these is negative, our product has to be negative. It peaks and it crosses zero because our current is zero. And now we have both positive. Voltage and current are both positive, so our power is positive. And so again, we get this cycling reactive power curve, and it's going at twice the frequency of our fundamental curve of 60 hertz. This one is 120 hertz, but the average value of that waveform is zero. All right? So that's the whole point of what I talked about. The power is oscillating back and forth. Okay? The average power consumed by a reactor is zero over time. Now, of course, we need the other side of the equation. We've talked about, we've got the exchange between kinetic energy and potential energy, and this is the reactive part of the equation. But what's really good is that if we look at a capacitor, then in that particular case, the current actually leads the voltage. Remember where I said the current leads the voltage because I've got to have a finite current in this direction which builds up all the electrons on one plate and gives me an excess of electrons here versus a deficiency here. And then as I build up that charge, my voltage starts to increase. So intuitively, with a capacitor, the voltage lags the current. You've got to get the electrons flowing first, charge up the plate, and then the voltage increases as those electrons build up. So we see that. So let's look at this situation. We're starting out right here with a zero voltage, and so what that means is there's no excess of electrons on one plate versus the other. All right? But we've got a peak of current. So we've got current rushing into this capacitor, building up electrons on this plate. As those electrons build up, our voltage on this plate is increasing. So we've got all those electrons rushing in, and as they're rushing in, the voltage is increasing. And the rate of increase of the voltage, you see right here, there's a very high number of electrons rushing in, so our voltage is increasing very steeply. As our current comes down to zero, our voltage reaches a peak. So intuitively, I want you to understand is that the voltage is lagging the current by 90 degrees. You've got to get that rush of current going in to charge up the plate, and then the voltage follows after that. So the net effect is when you have a capacitor, a capacitor, the voltage leads the current. So we show that in that, in sequence, we have the current, and then the voltage is lagging it. And in a vector diagram form, we show that is that the current vector here is leading the voltage by 90 degrees. And again, let's look at the power equation. The voltage times the current is shown by the purple curve, and this is building up, coming back to zero, and oscillating at twice the actual frequency of the fundamental voltage frequency. And the really good thing is you notice that This voltage waveform is peaking within the first 90 degrees. And this voltage waveform with the inductor was peaking in the negative direction for the first 90 degrees. So they literally cancel each other out. And that's why you've got the two parts of the energy equation. You've got your power being absorbed by your inductors, and that can actually be complemented exactly by the power that is being generated instantly by your capacitors. And so that's why I draw the analogy between you've got the potential energy, which can be the energy in your capacitors, and your kinetic energy, which can be the energy in your inductors. And those two forces are oscillating back and forth between each other at 120 times a second to have an exchange of energy in your system. But there's no net dissipation of power. There can be huge currents flowing, okay, and there can be some losses due to those currents, analogous to the friction, but you can have a huge amount of magnetic power oscillating or sloshing back and forth between your capacitors and your reactors, and there is very few net losses on the system. In fact, what we like to do is we like to put those capacitors right close to where that inductive power is absorbed. So you will see capacitors right next to your distribution systems to compensate for all the customer loads that are drawing reactive power. You'll see huge capacitor banks next to high voltage, heavily loaded transmission lines, because as we'll get into, we'll show that those lines have a huge inductive demand on the system. So we summarized all that with the acronym, or the saying, Eli the Iceman, okay? This is an initiation into the world of power engineering, all right? If you talk about Eli the Iceman, then it means that you basically understand reactive power, because the voltage leads the current when you have an inductor, which is L. The current leads the voltage when you have a capacitor. Fortunately, today we have a good supply of electricity, and we have refrigerators and freezers, and we don't have to have Eli the Iceman visiting all the homes and stocking up your storage. But it's still a great acronym to understand reactive power. And there's actually a book out written by Eli the Iceman, a pseudonym, a retired power system operator, on an introduction to power systems. So I also recommend that for some entertainment. Now, there's another important concept, and that is the phase angle between the voltage and current. We covered the simple cases. With resistor, no phase angle at all. Reactor, the phase angle of the current lags by 90. Capacitor, the phase angle of the current leads by 90. If we have a combination, if we have a resistor and in parallel with that we have a reactor, we get phase angles between the range of 0 to 90. Here's one where it's actually at 45 degrees. And so what's happening in this case, a certain amount of current is going through my resistor, and that current is in phase. Another amount of current is going through my reactor, and that's out of phase. You combine those together in a vector sense to get the total current here in red. And in this particular case, then, our red current is lagging our voltage by less than 90 degrees. It's actually 45 degrees in this particular case, which means that this vector would be equal to that vector. So the phase angle is what we call the angle between the voltage and the current. You'll hear a term called the power angle. The power angle is that's really the angle between two ends of, that's the voltage difference in the angle of the voltage at two ends of a transmission line. So you need to have a good understanding of the difference between phase angle and power angle. Now, we can take this voltage waveform here and this current waveform, and we can actually decompose it. We can separate a sine wave into two, what we call orthogonal components. We can say that this vector here is basically composed of this vector plus this vector. In other words, if you were to go 300 miles in this direction, 400 miles in that direction, the actual distance you've traveled as a straight line between the 2 points is 500 miles. You get that from what we call the 3, 4, 5 triangle. So we can do a very similar thing with we can add current waveforms that are 90 degrees out of phase with each other, very similar to how you can accumulate distances when you're walking in a two-dimensional geographic plane. So what we do is we take this red waveform and we break it down into the green one, which is right in phase with the voltage. This is the voltage, this is the current. And the other component is the orange one, which is 90 degrees out of phase. So basically, the orange plus the green will sum up to give you the red. And you can verify that, okay? At this point, green is 0, so my red is just the orange. At this point, my green is peaked, my orange is 0, and so our green is equal to the red at this point. And at this point, we're summing these two values to get that. So it's just take it on faith that we can break a sinusoidal waveform down into two orthogonal components, 90 degrees separated from each other. Now, the beauty of that is we can then say that this voltage and this current is composed of a component of current which is in phase, and so that creates a real power loss. That gives us our real power when we multiply the green by the blue. We've got real power, and then when we multiply the orange by the blue, we have reactive power. And so we break that down into what we call the power triangle. We can say in any given situation, we have a certain amount of real power, or megawatts, and we have a certain amount of reactive power. And that's the fundamental. And then we talk about the complex power as the vector sum of these two. So basically what we're doing is we're going from a situation where we had a voltage and a current that are out of phase, and we're actually creating a reactive power and megawatt power triangle out of that. There is a slight transformation. We talked about how when we have an inductive circuit and a resistor, the current is lagging the voltage. But then we use the convention that for a lagging situation gives us positive power. When we have a generator feeding an inductive load, we call that positive power. And in the vector diagram, we like to represent positive power as things going up in a northerly direction. So there's actually a little transformation, as whereas my current was leading in this direction, we actually transform that into a positive power going up in a northerly direction. So when you see a vector like this, that represents an inductive load, and to compensate that with a capacitor, we would have a reactive power going in the other direction. But this is really the essence of reactive power management, what we call the power triangle. And again, it's something that it's important to understand this for your NERC certification. It's important to understand this to operate a power system, all right? It's a certain level of understanding that we all need to get through, because things like reactive power triangles, reactive power, are concepts that are not generally well known, but they are really fundamental to understand how a power system operates and how you're going to manage those voltages, all right? You've got to understand that so that you're not just doing things in a rote mechanical sense, that you truly know what is happening when you add that capacitor. You truly know what is happening as that transmission line gets overloaded. And the fact that there are very high current flows. In fact, we use the term megavars and megawatts because we're dealing with very large quantities. And then we talk about the apparent power, which is MVA. The MVA, the complex power S, is P in this direction, plus J. J is an operator that just rotates things by 90 degrees. So all we're saying here is that we've got a certain amount of megawatts, and then we have a certain amount of reactive power. Don't get confused by the J symbol. The J symbol is just analogous to the fact that the west coast is over there, the east coast is over there, all right? So I travel 100 miles from the west in an easterly direction. The J operator then simply says that if it was J100, I'm then going to travel north 100 miles, all right? So you'll see this, electrical engineers use this J operator a lot, and I just want you to think through. All it's really saying is that when we don't have J, we're basically traveling across the map, and then we have a J operator, we certainly turn around and we go in a northerly or a southern direction. So if it's a plus J, it says go in that direction. If it was a minus J, it would be go in the other direction. So that's really all the J operator does. But the thing that's really important for you as system operators to know is that it's the length of this. This is the vector that determines the current. The current in the actual conductors is proportional to the net current flow. And so you have to take the megawatts squared plus the reactive megavars squared, add them together, take the square root, and you get the length of that S vector. And we call that apparent power, MVA. And that's fundamental, because that's what loads up your transmission line. That's what causes the heating effect. So your transmission lines can be heavily loaded due to the combination of the megawatts and the megavars flowing. And you've got to anticipate both those types of components flowing in your transmission lines. And there are cases where you may have 200 megawatts of real power flowing, and you may have, due to the way the voltage is set up, you may have 100 megavars of reactive power flowing down your line. And you can unload that line just by controlling your voltages. In fact, if you bring that reactive power from here down to here, you're going to unload that line significantly. So there's a lot. The power triangle is not just a mathematical gimmick. Okay, it's what is you operators really need to understand to figure out what is the total MVA, megavolt amps. The product of voltage times amps is the square root of the megawatt squared plus the megavars squared. So it's a very practical tool, and it's very important that when you're looking at your transmission lines and you're seeing them on your SCADA diagram, you look at the megawatts and you look at the megavars. And the thing is that those transmission lines can be net producers. They have a capacitance. They can produce megavars. And so literally a transmission line at light load will be pushing megavars out both ends. But then as that line gets loaded up, it turns into has a net inductive effect, and it can be absorbing megavars from both ends. And as an operator, you've really got to understand that in fact, you have to watch the megavars at both ends. The megavars at each end can be different, and the MVA at each end can be different, and you can have a different heating effect at each end of the transmission line. And so it's fundamental that you not just look at the megawatts, you also look at the megavars. And so, yeah, that's a good point, that at one end, I could have 0 megavars, and I'm under the rating. At the other end, because it's a net absorber, I could have a very high amount of megavars, and those conductors at that end could be overheating and sagging. So you've really got to watch the megavars at both ends. And like I said, the megawatts are a nice uniform thing. What comes out will be a little less than what goes in. Megavars are totally nonlinear, because that line can either absorb or produce megavars. And we'll get into that whole characteristic a little bit later. Now, what we like to do is we like to define a power factor, which is basically the cosine of that angle theta. And the cosine of that angle theta is really that vector P divided, the length of that vector divided by the length of the vector S, all right? Basic trigonometry. The sine of an angle is that vector divided by that vector. The cosine is the adjacent. It's that vector divided by that vector. So for a pure resistor, this vector would be totally in phase. And so cosine would be 1 because it's that vector divided by that vector. They're totally in phase, so my S vector would be the same length as my megawatt vector. For a pure inductor, they're out of phase. And so in that particular case, I have 0 megawatts. And so my cosine for a pure inductor is 0. And my cosine for a pure capacitor is also 0. And typically, you'll have loads that are, the power factor can be anywhere from 80% to 99%. So, and that's just a shorthand way of talking about the relative. We primarily apply power factor to loads. Power factor for loads in the summer, they're a lot lower. In the winter, where it's primarily heating, you can get very high power factors in the 98% range. As you get into summer conditions with lots of air conditioners, those power factors can drop to the 90 to 80% range. All right, let's review. We've described the need for reactive power, where it comes from, basically either from inductors or capacitors. We've described the difference between how real megawatt power flows versus reactive megawatt power. We've described how real and reactive power vary instant by instant in real time as the AC waveforms are going up and down. We've covered the real and reactive power triangle, a fundamental tool for understanding the difference between megawatts, megavars, and MVA, megavolt amps. MVA is proportional to current. That's what is the limiting factor due to thermal ratings on equipment. We described how the current can be decomposed into a waveform that's in sync with the voltage and a waveform that is 90 degrees out of phase. And that leads to the real and reactive power components. And then we finished up with the definition of power factor. Thank you.